Hi, what I'm going to show you in this video is how let's understand what linear programming is. If you're already familiar with linear programming, you probably know what it is and how you can solve problems using linear programming. But if you're not familiar, I highly recommend you to read the theory first. Areas such as engineering, finance, and computer science, all kinds of engineering areas is heavily used. So it's more about optimization, okay, optimization of functions. But here in this case we are talking only about linear functions. You could also want to optimize a non-linear function, but we will see in a later lecture as to how we can do that. But linear programming is all about optimizing linear functions. We'll take an example. Okay, so here is this example. We want to maximize this function 2x plus y subject to a set of constraints. So we have got three inequality constraints. One is 2y plus x should be less than or equal to 22. The second constraint is negative 5y plus 4x should be less than 15. And the third constraint is negative y plus 4x should be less than 12. So that's the third constraint. And the last one is actually not the inequality constraint, it's the equality constraint, which is negative y plus 4x should be equal to 16. And there are two more constraints. Both x and y should be positive. It should be greater than or equal to 0 or a positive number. So what do we want then? We want the value of x and y that satisfy these constraints, and we want to maximize j in such a way that these constraints are satisfied, and yet the value of the function is maximum. Okay, so x and y are the decision variables. So we want values for x and y, so we call that as decision variable. The function that is to be optimized, when we say optimize, it could be minimized or maximized. In Python, actually we can only minimize, not maximize. But you can always convert a maximization problem to a minimization problem and a minimization problem to a maximization problem. So that's always easy to do. But remember one thing, that not all LPP problems have got a solution, proper solution. You will have a linear programming problem, in short known as LPP, that does not have a solution, right? And this situation arises when you cannot find values for your decision variable that satisfy all the constraints. That could also happen, that you will never have a solution for some of the problems. But if there are values for your decision variable that can satisfy all the constraints, then we can term them as solution to the problem. How do we solve it in Python? Okay, now we have taken this example, right? We'll try to solve this in Python. So we'll try to find out the value of x and y that maximizes g subject to this three inequality constraint and the one equality constraint, also ensuring that both x and y are 0 or a positive number. So we will import this linprog function from scipy. So from scipy.optimize we import this function. As I said, this linprog does not allow maximization, so we have to convert a maximization problem to a minimization, but that's easy. What you do is that simply change the sign for each of the variables. So instead of maximizing g equal to 2x plus y, we want to minimize negative of g. So simply it changes the function, you simply multiply a negative, so it becomes now negative 2x negative y, right? Also note that linprog, this linprog function does not allow greater than equal to. It always allows less than equal to. If you have greater than equal to, you can change the sign and convert to a less than equal to. So that's also possible. But in this case, we do not have greater than equal to constraint, so there's no issue. Okay. Then we have to define some variables before we use this in-pro function. So how you do that? So we have to first, this is one variable where we put the coefficients of the objective function. And what is our objective function? Negative 2x, negative y, right? So what are the coefficients here? Negative 2 and negative 1, right? So here we put it in a bracket. Okay. Then we have to define another variable. We call it an LHS. So we have to then put all the coefficients for these constraints, the inequality constraint, into one set of in one vector form, right? So here you see this coefficient. For example, for the first case, it's 2 and 1, right? Only LHS side. RHS side we'll see later. We'll define in another variable. But in the LHS side, we only have 2 and 1 for the first inequality constraint. For the second one, we have negative 5 and 4. For the third one, it's negative 1 per flow, right? So that's exactly what we have here. And then we have RHS side, okay, but only for the inequality one. There is also an equality constraint, but we have to make a differentiation between the inequality constraint and the equality constraint. And remember, when we talking about inequality constraint, it has to be less than equal to inequality constraint. If you have greater than equal to inequality constraint, then you have to convert that to a less than equal to inequality constraint. Okay, similarly you take that for RHS. Okay, so for RHS we have 22, 15 and 12. Okay, and that's what we have. Now for equality constraint. So the last equation is the equality constraint, right? Negative y plus 4x is equal to 16. Just to make a differentiation between inequality constraints and equality constraint, I'm using this prefix EQ. Okay, and the coefficients are negative 1 and 4. Like how we did for inequality constraints, you can also get these coefficients. That's LHS, and the RHS on the right hand side of the equation, you have 16, right? So here we assign 16. Just to confirm you again, so 16 is taken from here. It's the right side of the equation, right? It's as simple as that. Okay, but ensure that the order of the rows and columns is exactly same as you have in the equation. If you change the order, then it becomes a problem, right? So make sure that you have the order perfect. I mean, you can't just change 20. You can't just take 22 to the rightmost part and bring 12 here. That's going to be then wrong. You'll have a wrong solution in that case. So order has to be exactly same for both LHS and RHS. The next thing is about the boundary of the decision variable. So decision variable in this case can take only 0 and a positive number, right? It has to be above equal to and above 0. But in some cases we might allow any number from negative infinity to positive infinity, but that's not the case here. So here we have to define. So we take another variable, boundary variable, and we define that it should be within 0 to infinity. Okay, both x and y. Now you could have different boundary conditions for x from that of y. That could also be case, but not in this case. For both x and y, it has the same boundary condition. But remember one thing here, that for linpro function, it always takes 0 to infinity by default as the boundary condition. So it exactly matches our requirement, but it's not going to be the same all the times. So you have to make the adjustment accordingly, right? If the boundary condition says that okay, it has to be between 5 to infinity, okay, and y will be, let's say, 7 to infinity, then we have to make this change. right? So by default you will have 0 to infinity, positive infinity. So even if you don't use the boundary variable, it's still going to work, but I'm just defining this just to show you an example, and you can use that in case where you have to change the boundary condition. Instead of 0 you want some other value. Okay, finally, once we have defined all our requirements for the optimization, we will fit them into the optimization function. So lean prog is the function. Okay, we have to be very careful about the syntax. Okay, C is nothing but the objective function, and we have given the coefficients of the objective function in this variable called obj, right? And that's what we have given here with a comma. Then you define the upper bound basically is the inequality constraint, the LHS part first, and then the RHS part. Okay, so that's inequality part. Then for the equality part, you have A underscore EQ equal to LHS underscore EQ. Now this is coming from our own definition. Now you can give any name, okay, but make sure that you make a differentiation between inequality constraint and the equality constraint. Then B underscore Q. By the way, this A underscore Q, B underscore Q, these are keywords, so you can't just change on your own. I mean, these are the keywords you have to use. And then bounds is the B and D. Okay, a B and D is something that we have defined. You can just give any name. It's a boundary condition, right? And the method, there are various methods which you can use in a linear programming problem. In this case, I have used simplex. You can use other methods also. For example, you have interior point methods also. You have revise simplex method. I have used simplex. Okay, there are 3 methodology. You can also try out how the values of your decision variable x and y differs if you change the method, right? In most cases you don't change. If you have a perfect solution, then you will never have a difference between values of your decision variables, but that might change in certain cases. Okay, now we will run the code. Okay, so let's quickly run this. So boundary condition is to run. Now we will run this. Okay, so then we should be able to understand the results from this run. What it says is that success is false. If success is false, that means the optimization did not succeed. So there is no solution, reliable solution for this problem. Okay. If success is true, only then you have a reliable solution for this problem. Okay, a solution that satisfies all the constraint, right? And what went wrong is something explained here. So in the message it says why it is unable to give you a solution, right? So as I said, optimization problems need not always be feasible. Sometimes they are infeasible because you do not have proper solution for some problems, and these are infeasible problem. In this case, it turns out to be an infeasible problem. But I'm just experimenting. Maybe this equality constraint is actually creating the issue. Maybe if you can get rid of this, then we'll have a solution. So I'm trying to get rid of this equality constraint, but all the 3 inequality constraints are still there. Okay, so I'll just remove them, and let me run it again. And here you see success is now true. Okay, so when we just made a bit of a change in the optimization in the constraints, it is now working. Okay, maybe the equality constraint was too strict a constraint for this problem, but now after removing it we have solutions for x and y, right? So what are these values for x and y? Here are these values, 8.4 and 5.1, and success is true. Number of iteration is 4. Okay, fun is basically the value, the minimum value, right, at which the program converts, or the optimization routine converts. Okay, can we change the method and see whether we get different results? So we change it to revise simplex. Okay, that's interesting. So we got different numbers now, and so now it's x, the values are 11 and 0. Quite interesting. And then interior point. Okay, if you do not use the by default interior point methodology is used. Okay, let's remove this, and probably we will get a different result. Okay, so it's 8.9 and 4.1. You know why this is happening? Because we are having multiple solutions to the problem. It's not that you'll always have a single solution. You could also have more than one solution to a given optimization problem, right? And depending on the methodology for optimization, you are getting different solution. So some optimization problem will have more than one solution, and that's exactly is the case here. So the next video I'll take more real world problem. I'll probably take an example from inventory management or something else, something related to manufacturing, because manufacturing is one area where optimizations are used quite heavily. So I'll take more real world problem next time to show you how we can do it in Python. Thanks. Welcome to the second part of the linear programming using Python series. So in this tutorial we will learn about how to solve a real world linear programming problem using Python. So let's do a brief recap of what we learned in the last tutorial. We started with a brief theory of what is linear programming. So in linear programming we try to maximize a linear function subject to some constraints, right? So what we do is we formulate the problem. We have the objective function. So this is the objective function. Either we want to maximize it or minimize it. In Python, actually in SciPy, the maximization facility is not available, so we have to convert that to a minimization problem, which is very easy to do. Then we have set of constraints. So again, we define this constraint in equation forms, so that's easy to understand. So we then provide the information. Basically, we provide the coefficients of the objective function and the constraint to the Python module, and it solves for us. So it gives for what value of x and y we optimize the objective function. Okay, and optimization could be either maximization or minimization. In a real world setup, we could be, let's say, maximizing profit in the case of a manufacturing problem, whereas we could be minimizing losses or minimizing cost, right? So we can formulate in whatever way we want, and depending on the problem at hand, either we'll maximize or we will minimize, and both come under what is known as optimization. And we need to take into consideration the constraints, right? In a manufacturing problem, constraint could be constraint on manpower, constraints on raw material, or constraints on warehouse capacity, things like that, right? So these are some of the things which will be constrained in a more manufacturing related problem. And how we solve it? Well, we import the SciPy package. In SciPy, SciPy.optimize, we import this function called leanprog. Okay, and once we have formulated the problem like this in a mathematical form, like how I see here, we provide input to the function, the leanprog function, with some in a matrix form. So we first define the objective function. Okay, so you can convert a maximization problem to a minimization problem just by changing the sign. Okay, so it was plus 2 plus 1, we just converted to minus 2 minus 1 and became a minimization problem, because leanprog function in Python only minimizes, it cannot maximizes. So it's nothing but just change the sign of the coefficient, a maximization problem becomes minimization problem. So in essence we get the same, right? So when you maximize a negative, you actually minimize the positive, and the other way around, right? And then we provide the coefficient of the LHS, which is nothing but the coefficient of the left hand side of the equations. We provide that in a matrix form. We also provide the right hand side, right? Right hand side in this case is, let's say, 22, 15 and 12. Left hand side, okay, 2 and 1, minus 5 and plus 4, minus 1 4, minus 1 4, right? So these are the left hand side of the matrix, and then we have right hand side. We provide that separately. Okay, we could have inequalities, but we could also have equality. That means where we have equal to sign, right? And then we call the function. We have the leanprog function, then we provide the objective function. This is the syntax, C equal to, and then you provide the objective function. The matrices that we have just defined here, right? OBG. So that's something we provide, followed by the A underscore UB, basically the inequalities. So A is the matrix that takes into account the coefficients of the left hand side. So we have defined this LHS variable here, right? So this is what we provide, and then we also provide the RHS. So this A underscore UB, B underscore UB is a keyword, so you can't change. Okay, but it's nothing but just LHS of the coefficients and RHS of the coefficients. And then you also have bounds. That means if you have constraint on your decision variables x and y, you can also provide boundaries there. In this case, it has to be the 0 and above, so we have this boundary of 0 to positive infinity for both x and y. Okay, so that's what we learned, and we have various optimization modules to use. For example, interior point, which is by default, and then your reverse simplex, and then you have simplex, right? So you have multiple methods to choose from. Okay, all right, so we'll take more of a real world problem this time around. Last time was more of an abstract problem. So this is the real world problem, and as I mentioned last time also, that linear programming is heavily used in manufacturing related setup. So here this problem, there are 3 products to be manufactured in a manufacturing unit, and we know actually how much the factory or the company makes profit from each one of these products. Okay, so there are 3 products, x1, x2 and x3, and for every single cell the company makes $10 from $10 from x1, $20 for x2, $25 from x3. Okay, so that's about profit from each one of these products. Total number of products to be produced in a day is maximum of 50. Well, actually it's 80. Okay, I just forgot to change this number. It's to be 80, and then we have okay. So total number of products that you can produce in a factory is 80 because of shortage of manpower. So that becomes our constraint. And the first statement here, right, here we saw, you know, how much profit you can make. So profit is just our objective function, right? We want to maximize profit, and you'll understand it better when I put it in a mathematical form, right? And then you have another constraint, which is raw material. So raw material is used for all three of these products, x1, x2, x3. For x1 you need 3 units of raw material. For x2 you need 2 units of raw material. Yes, for 2 units of, and for x3 you need 4 units of raw material. Okay, and there are total 200 units of raw material available per day. You can't have more than that. So that's another constraint, right? So given these two constraints, how do we maximize the profit? I mean, how do we, as in how many units of x1, x2 and x3 should be produced in a day, so that the profit is maximized. Okay, so it's as simple as that. You have 3 options, 3 products to be produced, and how many x1, how many x2, how many x3 you should produce. It's very simple to understand, given the constraints, given the constraint on manpower, given the constraint on raw material, right? And also, you know, you cannot produce negative unit of raw material. So all 3 of these products, x1, x2, x3 should be greater than equal to 0, right? So that goes without saying, but it's also good to keep it in mind. So here is our objective function. We want to maximize 10x plus 20x2 10x1 plus 20x2 plus 25x3. So 10 is the profit from x1. Okay, x1 is the number of product from x1, so you just multiply. That's the profit you make from x1. Then you have 20x2, that means 20 is the profit from each single product of x2, and then x2 is the number of products of x2. So you know, you multiply that to get the profit, and similarly for x3. And when you add them, you get the total profit that you make from these 3 products, subject to the manpower constraint and the constraint on the raw material. So the manpower constraint is where, you know, in a day you can produce a maximum 80 products. So you need to then decide how many x1, how many x2 and how many x3, but total is known, has to be less than equal to 80. So that's our first constraint. The second constraint is that on the raw material. So for x1 you need 3 units of raw material, for x2 you need 2 units of raw material, for x3 you need 4 units of raw material. So total of raw material in a day available to you is 200. Hence 3x1 plus 2x2 plus 4x3 has to be less than equal to 200. It cannot go above that. So that's the limitation. And all 3 x variables should be greater than 0. That means we cannot have a negative number of products, right? So it's obvious. Okay. So we will also use linprog this time. Is something we have imported from scipy.optimize. Now this is a maximization problem, right? We need to maximize the profit. However, linprog, as I mentioned, is unable to perform a maximization. So we have to convert that to a minimization problem. So it's very simple. Simply multiply -1, right? Just change the coefficient with the sign, and you will convert that to a minimization problem. Although in essence it is a maximization, it's just that, you know, the maximization in minimization are interchangeable if you change the sign. Okay, but the objective doesn't change, it's the same. We still maximize the profit. So we are simply minimizing the negative part, right? So which in principle is nothing but maximizing the positive part, right? You change back the sign, it becomes a maximization problem again. So okay, so this is what we are minimizing, right? And then we need to provide the coefficients of the objective function and the coefficient of the constraints to the optimization module. In this case is linprog. Okay, so here we provide the coefficients of the objective function. Okay, so -10, -20 and -25. So we provide in a matrix form. Then you have coefficient of the LHS, right? You remember how we did last time around? So there are two constraints here, right? The first constraint on manpower, second one on raw material. LHS would take all the coefficients from the left hand side of the equation of the inequality equations and take the coefficient. So it's 1 1 1, right? In all three you have the coefficient of 1. So that becomes the first matrix, first element of the matrix for LHS, and the second one is 3 2 4. So 3, right? Look at this equation. So first coefficient is 3, second coefficient is 2, third one is 4. So we put that in a matrix from element, second element, right? So that's our LHS. LHS is about the right hand side of the value in the right hand side of the equation. 80 in the first case, 200 in the second case, right? So we put that in a matrix form. So here is, right? By the way, these are not keywords, so you can change any to any name, so up to you. Then you have boundary conditions. In this case, it's not needed, as I mentioned in the last video, that by default in LeanFrog your boundary condition is from 0 to infinity, and in this case we have this boundary condition of 0 to infinity. That means it has to be positive, 0 or any positive number. But if you want also negative number, you want to change this default boundary condition, you can also do that. But here we don't need that because by default it serves our purpose. Finally, we will then do the optimization. So using the LeanFrog function, here we provide the optimization routine with the coefficient of the objective function, right? C equal to obj. So this is something we have defined over here. So this matrix is then given as an input, A underscore UB and then B underscore UB. Basically this is the matrix for the left hand side, this is the matrix for the right hand side. Okay, so if you are familiar with linear programming, mathematics, you can very well understand it's just a matrix, right? A x equal to B, so you want to find x, right? So if you remember your matrix algebra, it's nothing but A inverse B, something like that, and you find inverse of x, right? So it's something similar, okay, but you may not have closed form solution everywhere, so we therefore use optimization routine, right? And method, we can have multiple, you can use other methods, but we use simplex. Okay, and let us run this part. Okay, so it's just 5 lines of code and you're able to solve. So it says optimization terminated successfully. How many iterations? 3 iterations were needed. Success, here you need first thing you need to check here is whether it's success equal to true or false. If it is false, then there is no feasible solution for this optimization problem. Now not all optimization problem will have a feasible solution all the time. You may have problems where you do not have any feasible solution, so that's not the case here. It's true, so that we have a solution, and it's successfully terminated. That means the values we get are reliable enough. Alright, so what are these values for x1, x2 and x3? That means, remember what our question initially we asked ourselves, how many number of x1, how many number of x2 and x3 we should be producing in the factory, and for maximizing the profit. It says that we should be producing 0 number of x1, 60 x2 and 20 x3. Total has to be 80, right? So it's divided 0, 60, 60 and 20. So the most profitable product is x2. That's what it's saying. So that's one thing you can get to know, that the product you should be maximizing on is x2 because it's giving you more profit, given the constraint. So that has to be also be considered. And the product that is giving you least profit is x1. So optimization routine is telling us not to produce that at all, and in between these two is x3, which is giving us some profit, but not as much as what we are earning from product 2. So, product 3 is not that profitable, but it is more profitable than product 1. So, that is the combination we should be going for. Right. So, now in a more real world problem, you will have many more constraints. It is not just this 3-4 constraints, you will have many more constraints. And you will probably have many more products also. It need not be just 2-3 products, it could be also 10 products, and so it becomes more complex actually, but the formulation is exactly the same. So, you can expand it to a much bigger problem, it will still give you the answers. The formulation is exactly the same. So, you can play around with this script, and if you need this code and the Python script, let me know, I can also share with you. You can find my email in the description. Thank you. Welcome to another video on linear programming in Python. In this video, we will see how to perform mixed integer programming in Python. So, what is mixed integer programming? In short known as MIP. Well, it is a problem where we have some conditions on the decision variables x, y. So, the decision variables have to be integers, they cannot take fractions. So, your decision variables cannot take values like 2.5 or 3.6, they have to be integers. So, that is one extra constraint that we add to the linear programming problem, and for that we use mixed integer programming. Here is this example. We will take this example to see actually how we can actually do that. So, it is a maximization problem. The objective function is x plus 8y, and we want to maximize this with respect to few constraints. So, the first constraint is x plus 6y must be less than equal to 15, and the second one is x should be less than equal to 4. So, these are the two constraints we have, and let us try to see how we can maximize the objective function x plus 8y given these two constraints. In this video, we will actually install the OR tools from Google. So, this is a tool created by Google for optimization purposes. So, we will not use the previous ones, right. In the previous video, we use some tools from scipy.optimize. We will not use these tools. We will rather use a tool from Google. It is called OR tools. You can install it first. So, this is how you install. So, this is not automatically there in Jupyter. So, you have to use pip install. This is how you install in Jupyter. And from there we will have to import what is known as pyrap LP. Okay. So, or.tool.linear_solver, we import this wrapper pyrap LP. Remember one thing, that the underlying solver is external, it is not something Google has developed, it is using some open source solver. So, one that is used is SCIP, but you can also use other solvers, and you can also write your own solver and call that. But the idea is that you can use any solver using this wrapper and solver in mixed integer programming problem. Okay. So, here we call this solver, as I mentioned, this SCIP is an open source solver that Google's wrapper is using. So, first we define the decision variables. So, in this case we have two decision variables, you could have more than two also, x1 y, and the syntax is very simple. We use solver.int var, and we provide what is the minimum value. Here the minimum value should be 0 in this case, because we want them to be positive. But you can also define anything. You can also define like, okay, negative infinity to whatever value you can take. Okay, it's very similar to how we use the optimize function module from the SciPy package. Very similar syntax. But remember, this in this case we can use both maximization and minimization, whereas in SciPy it's always the minimization. So we have to convert a maximization problem to a minimization problem there, right? So if I haven't gone through these two videos, I highly recommend you to go to the first two videos where I have used SciPy package for optimization. And then we will define the constraints. The two constraints, x plus 6y should be less than 15 and x should be less than equal to 4. Syntax is very simple, solver.add, and then in bracket you basically define your constraint. It's very easy, right? Whereas in SciPy the syntax is a bit more complex, I would say, right? You have to provide the coefficients in a matrix form, right? If I've gone through the other two videos, the first two videos, then I'm sure you know actually what I'm talking here. So here the syntax is a bit easier to understand, also to okay. The second constraint, x is less than equal to 4, same syntax. Let's run this. Okay, I think we have not run this yet. After that you define the objective function. So in this case it is x plus 8y. Syntax is solver.maximize, and if it is minimization, just write solver.minimize. It's a maximization, so we'll write maximize. We run this, then we will solve it. Okay, and then we store it in status, and then we will use some sort of syntax to print the result. So this it's very easy again. If the status is optimal, that means there is a solution, then it will provide you the solution. Otherwise, what we print is that the problem does not have an optimal solution. So only if there is an optimal solution we get the results, otherwise we won't. Right, so here we go. So the value of x is 3 and the value of y is 2, and both are integers, right? You will never get something like 3.5 as an answer or as a value to your decision variable, or 4.6. Always integers, because this is mixed integer program. All right, what would have been the answer if we had to use the linear programming, the more normal linear programming, right? What values would have maximized this objective function? What we will do is that we will just change the solver. Instead of using a mixed integer solver, we will use more of a linear programming, a normal linear programming solver, which can also have non-integers as decision variable. So here we use this GLOP. Okay, so this is not mixed integer linear programming, this is the simple linear programming. So it can have non-integer values for the decision variable. So we run it again, and then we will okay, we will solve this, taking some time. Okay, there is some issue. I have to rerun some of the things, but that should be fine. We solve this and let's print the results, and here you see the solutions for this problem is x equal to 0, y equal to 2.5. So, 2.5 is not an integer, right. So, for a very simple if you use simple linear programming problem for this objective function, the solutions are 0 and 2.5, whereas if you use a mixed integer programming problem, you get values as x equal to 3, y equal to 2. So, that is how we use a mixed integer programming to solve a linear programming problem.